Hi, I'm Rajat Talak. In this talk, I will discuss some of my work on information freshness for networked autonomy. This is a continuing line of work that I started during my doctoral studies and has evolved since then. So, first, what do we mean by networked autonomy? This is a network of robots that can seamlessly communicate to jointly perceive, plan, and act in the real world. Now, there are many applications of this. Let us just see a few examples. This is an Amazon warehouse where robots basically have to ferry carts containing packages between entry point, storage, and exit. These tasks are coordinated and executed by hundreds of such robots in a single warehouse. This is another example of a team of robots exploring a subterranean environment. Now, DARPA between 2018 and 2021 organized a challenge where a team of robots have to collectively traverse and map an underground environment and search for some artifacts. The main challenge here was to cooperate and build a map of the environment that was kilometers in length. Self driving cars is another example of networked autonomy. Now, self-driving car has to perceive other moving cars, pedestrians, stop signs, and navigate traffic. Relying only on its own sensors may be limiting, and communicating with other vehicles in the vicinity can help extend its perception range. Robot swarms have also been investigated. These are large number of small-sized robots programmed to perform coordinated action. They were originally envisioned after emergent behavior like in things like bird swarms, but have evolved to include applications such as coordinated action in disaster relief. So now one of the promises of all such systems and network autonomy in general is that the network part is going to make things more safe and resilient. To see this, let us take the case of self-driving cars. We see that seamless exchange of information can help in road safety in self-driving cars. For example, here we see that the truck is able to warn the red car of an incoming vehicle and potentially avoids a collision. Here's another example where the white car informs the red car of a pedestrian crossing the street, thereby allowing it to stop right before it turns right. The thing to note here is that while safety and resilience are valid promises of networked autonomy, to reap them, we need seamless communication between robots. Now, one aspect of such seamless communication is the exchange of time sensitive critical information. So, for instance, in the video that we just saw, it was necessary to send the information about the pedestrian crossing the street in a time critical fashion. So, the question that we ask is how do we measure and optimize for such information? So, in the rest of the talk, I will explore this question. We will first discuss a way to quantify and measure information freshness. I will provide two reasons as to why we use the metric that we do. I will then give an overview of our work on optimizing information freshness in various network scenarios. And before we conclude, I'll briefly also touch upon the freshness delay trade off that we discover. So let us consider the first question of how to measure information freshness. So consider a very simple model in which autonomous agents or vehicles are just dots in this unit square, and each of these dot can travel with a maximum speed of v. Uh, for illustration, let there be just three vehicles, A, B, and C, and let delta B and delta C be the time since B and C communicated their relative positions to A. So given that A only knows that B and C travels at a maximum speed of v, from A's perspective, B and C can be anywhere in this union of two circles. So this region, the yellow region, we call it the uncertainty region, and define the fraction of times A enters this region as the hazard rate. Now we considered the problem of how communication constraints might affect this hazard rate back in 2016 in the CDC paper. We assumed a simple broadcast channel, that is, at a time only one of the n nodes in this unit region can send its location information. The interesting part was that we could show that the hazard rate follows a threshold behavior with respect to speed as n goes to infinity. That is, if the speed decreases slower than a particular scaling, there is no communication scheme that can ensure a hazard rate lower than 1. This means that the agent will always lie in its uncertainty region. But if the max speed decreases faster than the particular scaling, there is always a communication scheme that can achieve a hazard rate of 0, meaning no collisions. So we make two observations from this. First, in the paper, we show that a simple round robin scheduling policy meets the requirement. That is, it's always able to achieve the zero hazard rate when possible. And now this is good because most practical networks like Wi-Fi and 5G implement a periodic update of one kind or the other. So this justifies that. But on the other hand, this result may not be good enough. That is, analysis based on scaling laws may be weak to determine the best scheduling policy, as it often leaves out the granularities present in the finite n case. The So the second observation is the behavior of the uncertainty region. So if you just take a look at how the yellow region evolves and maybe just take a look at one vehicle, we see that the size of uncertainty region grows when there is no transmission, almost linearly, and reduces upon a transmission. That is when an update is exchanged. And the uncertainty somehow can be seen as the area under the curve. So, fortunately for us, a concept very similar to this was already developed when we uh, wrote this paper, and this was called Age of Information. And Age of Information is basically a time evolving metric which looks very much like what is shown here in the red lines. And it works as follows. So, a source generates updates, and at the destination, you measure the time elapsed since the last received fresh update was generated at the source. So, take a look at this graph. The age evolves linearly till it receives message 1, at which point the age drops to the time difference t1 dash minus t1, which is the time since the message 1 was generated at the source. Now, two things to note here about age of information. Uh, it is, firstly, the age is a time evolving metric, and the second is that it does not care about stale packets. So, for instance, in the figure here, packet 2 is received by the destination after packet 3. And because packet 3 contain fresh information than packet 2, reception of packet 2 does not cause any change in the age. So now, because of this similarity between the uncertainty region evolution and the age of information, we use age of information as a measure of information freshness, and then try to optimize it on a network of finite size n. Now, because age of information is a time evolving thing, we obtain two time average metrics to characterize how large or small age of information is. The first is the average age, which is nothing but the area under the curve. The second is the peak age, which is the average of all the peaks in the age curve. Now, before moving to optimizing the age metrics on on a network system, let us look at the behavior of age in a much simpler system and try to decipher it. So the first paper to analyze age was by Sanjit Kaul, Roy Yates, and Marco in 2012, and they basically analyzed a first come first serve queue and shows that the average age, uh, as a function of server utilization, looks like this U shape. So this meant that the average age was worse when the arrival rate was close to the service rate, as well as when the arrival rate was much smaller. Now, the right part of the U shape is similar to what we observe also in the delay plots, the average delay plots in simple queuing systems. The age is high here for the same reason the delay is high, which is the congestion. But the left part of this U shape was something new. And the question was, what can probably explain it? Now, there was a paper published in 2004 that explained this phenomena, but in a different setting. It considered Kalman filtering, which is basically a linear time invariant evolution of x that evolves like this: xt plus 1 is some times xt plus some noise. Um, and you do not observe x directly, but you observe y, which is some c times x. And the goal is to estimate the true state of x at any given time, given the current and past measurements y's. Now, there are known conditions on these matrices A, C, Q, R, which guarantee that uh, the estimate will have finite variance and things like that. So, for instance, if C is zero, then there's no way to estimate X given Y. So, what the paper showed that if instead you were to observe Y not at every time slot, but at uh, randomly in each time slot with probability lambda, that is in with probability 1 minus lambda, you don't observe yt, we'll have a threshold lambda c below which it will not be possible to estimate the state x. But more importantly, the paper also showed that as lambda approached lambda c from above, that is, as lambda became close to lambda c, the variance in the state estimate also exploded. Now, this phenomena was termed as the uncertainty principle. It basically says that when the sensor observations are too infrequent, it becomes impossible to estimate the state of the system. Now, the left portion of the U shape in the age curve has the same resemblance and can be thought of as an instance of this uncertainty principle. That is, the age worsens when you have two infrequent updates. So, this, according to me, explains the two sides of the age curve. The first side, the right hand side, is explained by congestion, and the left hand side is explained by the uncertainty threshold principle. Now, this paper on Kalman filtering and intermittent observations launched a new area of investigation on sensor scheduling networks, scheduling sensor networks. Um, and so, just a side question is that why not use this? Why do we do age of information? Why not? Because so this one will the Kalman filtering sort of approach will help us also model um, the dynamics more accurately, and probably we can do some sort of co-design. Why prefer age of information over this? So I generally give like three reasons for this. So the first is that if you do co-design, the co-design gets interactable very soon. uh, at a linear time system, even if you have the linear time invariant system, under different network conditions, it gets very hard to analyze. Secondly, it also assumes the knowledge of state and observation dynamics, like sensor dynamics, which is not really uh, uh, which is usually not feasible to obtain in all cases. The second reason is that the age, on the other hand, is much simpler to analyze and also encodes the same phenomena that is the phenomena of uncertainty threshold principle, as we just saw. And the final reason is that separating the physical and sensor dynamics from communication fits the system design principle of principles like layering and modularity, which have held the test of time. So this is the second reason why we use age of information as a measure of information freshness. So given this, we turn our attention to optimizing information freshness. In particular, we optimize age of information in wireless network, and nodes in the wireless network model autonomous agents. We consider various scenarios: mobile static nodes, single hop, multi hop flows, known and unknown channel state information during scheduling and routing, and different kinds of traffics like unicast, multicast, broadcast. The goal here is to develop scheduling policies to minimize age in all these scenarios. So what we'll do is we'll only consider static agents and explore all the other scenarios, and I'll provide an overview of the work that we have done in this. So let us consider a single hop network where each source destination pair is directly connected via a link, but the link suffers from interference constraints. That is, not all links can be activated simultaneously. We have so therefore we let A to denote set of all activation sets, which is the set of links that can be activated simultaneously. So in this setting, we propose three scheduling policies. First is randomized stationary policy. In it, we select a set M, uh, an activation set M, and transmit it with probability Pm. Uh, so, given such probabilistic description of scheduling, we can derive analytical expressions for peak and average age, and we obtain optimal probabilities by solving an optimization problem. The second policy is an age-based policy. In it, we prioritize links with higher age. We assign weight to each link to be the product of the channel state and an increasing function of age, G. Um, and we select an activation set with the highest weight. The third policy is a virtual queue based policy where instead of the age or a function of age being the weight, we use a virtual queue. We implement evolution of this virtual queue based on the current and past transmissions and use the product of the queue size and the channel state as the weight for each link. So here's an overview of results that we obtain in several papers. So when the channel state information is known, we show that the randomized stationary policy is peak age optimal and factor 2 average age optimal. We show that the age based policy is factor 4 optimal for both peak and average age, and the virtual queue based policy is peak age optimal. When the channel state is known, we see that the age based policy and virtual queue based policy retain their performance guarantees, theoretical performance guarantees. Empirically, however, we observe that the age based policy does much better. So, in terms of peak age, we see that all three policies that we described are peak age optimal, uh, but age based and virtual queue based policies are the best uh, for average age. Now, these sets of results assume that the fresh information is always available for transmission uh, when the transmission is scheduled. So, this is just like the Kalman filter intermittent observation. So, whenever we sampled, we had the observation y of t. However, in practical systems, this is not really the case. So the applications that require freshness operate at a layer higher than the transport layer in the communication stack, and the MAC layer queue, on the other hand, can build up if too many updates are generated uh, by the application, and this can lead to suboptimal performance. Now, note that there are two things we can control here: the packet generation rate and the scheduling. Now, confining to randomized stationary policies and unknown channel state information, we show that the following separation policy is nearly optimal. The separation policy basically generates updates at a queue utilization as if there were no other nodes to contend with in the network. And the scheduling assumes that the fresh information updates are always available at the source. And it turns out that such a separation policy turns out to be very close to optimal. So this graph here shows the performance of the separation policy, which is the red line, and we overlap it with the black dots, which is the optimal that we derive. So the setup that we considered thus far assumes a centralized scheduler that can activate links at will. We also consider a distributed scheduling setup. In it, the probability of successful transmission on a link will be lower than in the case of centralized scheduling due to contention. But we show that in the distributed scheduling setup, the age minimization problem can be recast as a distributed convex optimization problem and solved to obtain the optimal transmission probabilities. I refer you to this paper for details. Uh, but now let's move to look at the multi-hop network case, which is rather more interesting. Uh, So we consider similar setting as in the single hop in terms of the network and interference. But now the source destination pairs are separated by multiple hops. We also consider a more general case of the flow, that the flow does not merely flow from a single source to a single destination, but can have multiple destinations denoted by dk. We assume that each source K can commission a set of nodes Ck to forward its update packets to the destination node. And in particular, we consider all cases like unicast, multicast, broadcast. So for this also, in our work, we propose three policies. The first is again a randomized stationary policy in which we randomly select an activation set M with probability PM, and also assign a flow to each link according to a probability. Using this description, we derive peak and average age expressions and optimize uh, them to obtain the optimal probabilities. The second policy is called the age difference policy. So we basically work with the following heuristic, that keeping the age differentials between neighboring nodes low can minimize the overall age at the destination. So we assign a weight delta to each link, which is proportional to the age differential. So the age differential between on a link ij would be aj minus ai, which is the difference between the age. Okay. Uh, so we schedule the links by solving the max weight problem. So finally, we propose an age debt policy. So the intuition behind the age debt policy is as follows. If you somehow knew an achievable age, let's say an optimal age, alpha, uh, we would just build a queue by counting the age debt like this. So qi is equal to qi plus the difference between the current age minus the optimal age or the achievable age that we know can be achieved. Now, if you build age dead queues like this, then what happens is the problem of attaining that attaining alpha i's to be the average age becomes a s- queue stabilization problem. That is, the problem of optimizing age then becomes equivalent to the problem of stabilizing age dead queues, which is what we do, and we propose a scheduling scheme that minimizes the Lyapunov drift. It turns out that the age debt policy has several advantages over other proposed policies. It can work for any types of flows like unicast, multicast, broadcast. The second thing is that the age debt policy also works for with any nonlinear functions of age. So, for example, if we care about average of g of age, where g is some nonlinear function, um, then we just have to build dead queues using the same g function. Now, I mentioned that alpha is an achievable or an optimal age. This is hard to find a priori, but we implement two methods and show that they can help us determine achievable alpha online and show their good empirical performance in the experiments. So our experimental results suggest that the age debt policy is the best across various settings. So in the single hop setting, it does better when we use nonlinear functions of age, which the other policies do not know how to optimize for. The age rate and age different policies outperform randomized stationary policy in the unicast line network, the second figure that is shown here. And in the broadcast setting, we see that it performs better than other baseline approaches uh, that exist in the literature. The advantage of the age debt policy with respect to other policies is that it can operate under several settings like unicast, multicast, broadcast, and also uh, accommodate for nonlinear functions of age. So, in the last few minutes before we conclude, I would like to point out an important result that we obtained, and that was the age related trade off. So, age and delay are both measures of latency. And although age is information centric, whereas delay is data centric, the question is, can we simultaneously minimize age and delay? And the answer turns out to be no. It turns out that minimizing age can not only result in the worst case mean delay, but also worst case delay variance. So this plot here shows that the plots attain packet delay and average age for various queues, for including last come first serve with and without preemption, first come first serve, and various service disciplines. And we can see here that as if you want smaller average age, the packet delay has to be higher. So for this queuing setup that the figure of which is shown, we show that uh, as long as you control the routing and the service time distribution for up to a fixed service rate, that achieving minimum age can result in the worst case delay and delay variance. So now I won't prove the result, but I won't show the theorem. But the intuition behind such a trade-off is basically noting that there are two kinds of packets when you look at age more deeply. There is an informative packet and a non-informative packet. So non-informative packets is one which arrives late and does not reduce age. So packet 2 here in this example is a non-informative packet. So now what happens when you try to minimize age is that it prioritizes informative packets while not caring about non-informative packets. The delay, on the other hand, is affected by both informative and non-informative packet, and this results in the trade-off. So I would like to conclude here. To summarize what we discussed, we saw that a timely exchange of information is critical to enabling safety and resilience in network autonomy. We argued that age is a good metric for information freshness. We considered various scenarios and derived scheduling policies for minimizing age. Much of this has laid down the foundations for future work on deriving performance bounds. Finally, I want to say that there are a lot of open opportunities and open problems in this area. Age optimal policies are yet to be developed for many setups. So, what happens when the nodes are mobile, or how do we design distributed scheduling policies? Are all good open questions. There's also a need to explore the age relay trade off in different scenarios. And it would be good to take some of this work to real world implementation on robots. So on that, here is an interesting is a recent example. This is work by my collaborators, Vishrant, Igor, Nedza, where they show that the age optimal design can help reduce tracking errors in multi-robot systems. So do check that work out as well. Finally, I want to thank Vishrant here for he was the co-author in the multi-hop paper that we wrote recently, and some of the other works on age that I haven't included in this talk. So thank you.